Greetings to one and all. I am P.R. Narayan from the School of Chemical and Biotechnology, Shastra. In this short video, I will explain briefly the algorithm to solve a flow-through pipe problem, which is a type 3 kind of problem as part of the fluid mechanics course. Now, the objective of this problem is you have been given a volumetric flow rate or throughput. The pressure drop is given, and we have to determine the diameter of the pipe. So let us see the data given in a typical problem statement. The fluid properties are given, the density is given, dynamic viscosity is given, the length of the pipe is given, and the dimensionless roughness parameter is given. We have been given also the operating conditions, which is either it could be the volumetric flow rate or the mass flow rate, and the pressure drop or the power consumption. And we have to find the diameter of the pipe that fits to this data. Let's see the list of formula that can be used for this problem statement. Mass flow rate m dot can be written as density times the volumetric flow rate, and the volumetric flow rate q can be written as the cross sectional area, which for a circular cross section pipe is pi by 4 d square, and u bar is the superficial velocity, or for a single homogeneous flow this can also be the average velocity. The Reynolds number based on the pipe diameter is given as du rho by mu. We can replace the velocity in terms of flow rate and you will get this expression. Pressure drop delta P is written as Fd times half rho V square into L by D, and power can be written as pressure drop times flow rate. Now, depending upon the flow regime, we can have the laminar flow friction factor written as 64 by Re, or we have two correlations for the turbulent flow. One, which is a Blasius correlation, which can be used for a smooth pipe, and the other is a Churchill correlation for friction factor, which is used for a rough pipe in case if you have a roughness parameter. Now let's see the algorithm. First, we'll assume the flow to be laminar, and assuming the flow to be laminar, we will find the diameter of the pipe. Now if we assume the flow to be laminar for a circular cross section pipe, we can replace this Fd as 64 by Re, and this translates to an Hagen-Poiseuille's expression as given here. Delta P by L is 32 mu viscosity times the velocity divided by d square, and this velocity can be replaced in terms of flow rate. Now if you see this expression based on the problem statement, all quantities are known except the diameter. So we know pressure drop, we know length of the pipe, viscosity is known, volumetric flow rate is known. So the only unknown here is the diameter of the pipe, so you can calculate the diameter from the knowledge of all other properties that is given. Now we have assumed the flow to be laminar, so that means we need to check whether our assumption is valid or acceptable. Now how to do this? Based on the diameter that you calculate here, check for the Reynolds number, and if the Reynolds number is less than 2100, then our assumption is valid and the flow is laminar, and the diameter that is computed in step 1 is the diameter of the pipe that we have to use for this problem statement. Now if the Reynolds number is not less than 2100, that means the flow is turbulent, so the diameter that is computed using this expression is not acceptable solution. So in the first step we assume the flow to be laminar. Assuming the flow to be laminar, we calculate the diameter using Hagen-Poiseuille's expression, and once we calculate, we check for the Reynolds number. The diameter that is calculated using Hagen-Poiseuille's is acceptable only if the Reynolds number is less than 2100. Otherwise, this diameter is not acceptable, and we proceed to step 2. In the step 2, we know that now the flow is turbulent because here the Reynolds number is already not less than 2100, but we assume the pipe is a smooth pipe. So that means we don't take into account the roughness parameter that is given in the problem statement. We assume the flow to be smooth, and then we calculate the diameter as follows. Now we know this is the expression for pressure drop, and for a smooth a turbulent flow through a smooth pipe, the friction factor is given by a Blasius correlation, which is this. Now if you combine these two and you replace the superficial velocity in terms of volumetric flow rate, which is shown here, so I have combined, instead of friction factor I have written the Blasius correlation, and I have simplified by substituting the Reynolds number expression, and once again in terms the velocity is replaced in terms of volumetric flow rate, you arrive at this expression which is shown here. Now again in this expression all quantities are known, so we know the pressure drop, we know viscosity, we know the density, we know the volumetric flow rate. The only unknown is the diameter of the pipe. So from this expression we can calculate the diameter of the pipe. Now this is the diameter of the pipe provided the flow is turbulent and the pipe is a smooth pipe. So if the pipe is a smooth pipe, we can arrive at the solution which is based on this expression. Now let's go further. If the pipe is not a smooth pipe, so that means if we are given the roughness parameter, then the diameter computed using this expression in step 2 can be used as a guess value, as an initial guess for an iterative procedure to arrive at the actual diameter. So this is explained here. So we guess first the diameter. For the first time, we can take the diameter that is coming from the step 2 as the guess diameter. Then at the guess value of the diameter, we compute the cross-section area of the pipe. Then we calculate the superficial velocity and you calculate the Reynolds number. And then now because the pipe is a rough pipe, we use the Churchill correlation to find the friction factor. And once we find the friction factor, we calculate the pressure drop. Now once you calculate the pressure drop, you compare the calculated pressure drop with the pressure drop that is given in the question. Now if the deviation is less than 1%, then we assume that we have converged, and whatever is the diameter that is assumed in 3.1 step is the answer. In case if the calculated diameter based on the guess value of diameter, pressure drop based on the guess value of diameter is greater than the pressure drop given in the question, then that means we need to increase the diameter. So that means we are basically going for a larger pipe, and for the same flow rate, when you go for a larger pipe, the pressure drop will decrease. So you have to increase the guess value of the diameter and repeat the steps 3.1 to 3.7. Now if the calculated pressure drop is less than the given pressure drop, then you have to decrease, you have to constrict the pipe diameter. You have to make sure in the next iteration the diameter is decreased, and again you have to repeat the steps from 3.1 to 3.7. So this can be easily shown in the form of a tabular column. So I have an iteration, I guess the diameter, this is the cross-sectional area, this is velocity, this is a pipe flow Reynolds number, this is friction factor, calculated pressure drop, and this is a comparison between the calculated pressure drop and the given pressure drop in the problem statement. For the first iteration, we take the diameter as the one that is calculated as per the step 2, which is for a turbulent flow but through a smooth pipe. And for this value of diameter, we calculate area, we calculate velocity, Reynolds number, friction factor, and we calculate the pressure drop, and we compare. If the value is less than 1%, then we arrive at convergence, or otherwise we keep changing the diameter and we do it until this value is less than 1%. And if it reaches less than 1%, whatever is the corresponding diameter that is assumed at that particular iteration is reported as the solution. So I hope this tutorial helps you to solve type 3 problems in flow through pipes, wherein you have to find the diameter for a given volumetric flow rate and pressure drops. Thank you.